Swayam Prabha. Digital India. Educated India.
Today we will start the topic, that is dynamics of higher order systems. Dynamics of higher order systems. Previously we discussed the dynamics of first order system and then the dynamics of second order system. So today we will discuss the dynamics of higher than second order systems. Now systems higher than second order dynamics are not uncommon in chemical processes. Systems with higher than second order dynamics are not uncommon in chemical processes. Examples include the processes having n first order systems, connected in series. Fine. So we can say that we are presently interested to discuss n order system dynamics, where n is greater than 2. Now n order system dynamics, the examples include processes having n first order systems connected in series. Second example is processes with date time. Examples include processes with date time. Examples include processes with inverse response. So these are the examples of n order systems, and all these three processes we will discuss one by one. So first we will discuss n first order processes connected in series. First we will discuss n capacities in series. Fine. First we wish to discuss n capacities connected in series. So it has basically, we can classify this into two different systems. One is n non-interacting capacities in series, another one is n interacting capacities in series. So it is two we can classify these into two classes. One is n capacities in non-interacting capacities and another one is in interacting capacities. Fine. So, if we consider n non-interacting capacities, then we need to connect n first order systems in series. So, we will connect these n number of first order systems. The transfer function of the first system is Z1s. Input to this transfer function is, say, F1 bar S. Output of this first system is Y1 bar S. The second first order system has the transfer function of Z2S. Output of this second first order system is Y2 bar S. Like this, we place the last or nth first order system having transfer function of Gn. Input to this nth first order system is Yn minus 1 bar S. Output is Yn bar S. This is the n non-interacting capacities connected in series. So, what will be the overall transfer function? Overall transfer function of this n non-interacting capacities is represented by Yn bar S divided by F1 bar S, which is equal to Z1s multiplied by Z2s, like this, Zns. Fine. Multiplication of transfer functions from G1 to Zn. Now, what is the transfer function of a first order system? I mean, Z1 equals Kp1 divided by tau p1s plus 1. This form we derived earlier. Similarly, for the second first order system, we can write Kp2 divided by tau p2s plus 1, and last transfer function is represented by Kpn divided by tau pns plus 1. Fine. So, this is the overall transfer function for n non-interacting capacities in series. Similarly, for the case of n interacting capacities in series, we obtain more complex form. Fine. For the n interacting capacities in series, we can obtain the overall transfer function in more complex form. Now, we will conclude based on the dynamics presenting in a plot. So, this is the dynamics of different systems. Here we will consider height divided by Kp. Say this is the steady state value. So, for the first order system we get the dynamics like this. This is for the two non-interacting tanks in series. This is for two interacting tanks in series, and this is for 4 non-interacting tanks in series. This is the dynamics of first order system. See, this is the dynamics, this is the representation of dynamics of a series of tank system. Fine. So, the first curve represents the dynamics of a single liquid tank system. The second curve represents the dynamic behavior of two non-interacting tanks system. This is the dynamic behavior of two interacting tanks system, and this is the dynamics of 4 non-interacting tanks system. So, this is the representation of dynamics of liquid tank system. Fine. If we consider a single liquid tank system, then we get this type of behavior. For 2 non-interacting, 2 interacting and 4 non-interacting tank system, we obtain S-shaped behavior. S-shaped behavior, and as I mentioned in the last class, this H represents the height of first tank for single tank system. The height of H represents the height of second tank, and Kp represents the gain of second tanks for 2 tank system. H represents height, Kp represents gain for fourth tank for 4 tanks system. Fine. Now, we wish to conclude based on this observation. So, first we will consider the non-interacting case. First we will consider the non-interacting case. So, as I mentioned that we got S-shaped response. S-shaped response. That means the response has the characteristics of overdamped system. So, we can say that the response has the characteristics of an overdamped system, that is the S-shaped behavior, and the response is also sluggish. Overdamped means zeta is greater than 1, so the overall response is sluggish. This is the first remark. Fine. Second one is increasing the number of capacities increases the sluggishness of the response. If you compare the dynamic behavior of 2 non-interacting tanks and 4 non-interacting tanks, if you see the behavior of 2 non-interacting tank and 4 non-interacting tank, then we can conclude that increasing the number of capacities in series increases the sluggishness of the response. Agree? So, this is the second comment. Increasing the number of capacities in series increases the sluggishness of the response. Sluggishness of the response. Fine. This is the second conclusion we can make for non-interacting capacities systems. Similarly, if we can conclude for the interacting case as interaction increases the sluggishness of the response. If you again compare the dynamic behavior of two non-interacting tanks and two interacting tanks, which is providing slower response? Two interacting tank. So we can say, we can conclude that interaction increases the sluggishness of the response. We can conclude that interaction increases the sluggishness of the overall response. Fine. This is the conclusion we can draw for the case of interacting tanks system. So next we will discuss the processes with date time, which is also an example of higher order systems. Next we will consider the processes with date time. Fine. To discuss this topic, we will first take an example. Say this is a pipe through which a liquid is flowing. This is a pipe through which a liquid is flowing with the inflow rate of Fi, and say the outflow rate is F naught. Fine. Now we are introducing a change, maybe step change at a particular time instant. Suppose we are introducing a step change in Fi at time t equals to 0. Initially it is at steady state, I mean there was no change of flow rate with time. Now we are introducing a step change in Fi. Fine. So suddenly we cannot get any change in the output of F naught. If we give a step change at time t equal to 0 in Fi, at that time instant we cannot get any change in Fi. So we can also make one plot for F naught versus t. This is suppose representing time t equals 0. F naught changes after a time duration of Td. Fine. This Td is the time delay. This Td is the time delay. Fine. So if we introduce a step change in Fi at time t equals 0, at that time instant we do not get any change in F naught. F naught changes after a time interval represented by t suffix d, that is the time delay. Now, we will represent the time delay writing the number of blocks. Like, we can consider one block for a process. Input to this process is suppose Ft, fine. Output of the process is say Yt. Now, we need to include one block for date time. This time delay is again called date time, fine. So, one block we need to include for date time. What will be the output of this date time block? Output will be Yt minus Td, if Td is the date time. So, Td is time delay or date time. This block is representing a process. Input to the process is Ft, output from the process is Yt, and another block we have included for the date time. Output of the date time block is Yt minus Td. Now, we will represent this block diagram considering the variables in Laplace domain. So, this will be the process. Say this is a first order process. So, we can write the transfer function Kp divided by tau ps plus 1. This is the transfer function of the process, and we can say this is the transfer function of the first order process. Input to this process in S domain we can represent by this form, Laplace transform of Ft. Output of this process we can represent by y bar s, and this is the date time block. Output we can write Laplace transform of y t minus Td. This is basically Laplace transform of Yt, fine, and this block represents the date time in Laplace domain. So, what will be the transfer function of date time? What will be the Laplace transform of date time? Laplace transform of date time we can find by this way, Laplace transform of Yt minus Td divided by Laplace transform of Yt. So, this is exponential of minus Tds y bar s divided by y bar s, that means exponential of minus Tds, fine. So, this is the transfer function of the date time block. So, we can put here the transfer function as exponential of minus Tds, fine. Next, we need to determine the overall transfer function. What will be the overall transfer function? Overall transfer function. So, if we represent the overall transfer function by g naught s, then g naught s equals Laplace transform of Yt minus Td divided by Laplace transform of ft. Agree? This is the output of the overall system and this is the input of the overall system in Laplace domain. If we consider first order process, then the overall transfer function becomes Kp exponential of minus TdS divided by tau Ps plus 1. If we consider the first order process, then the overall transfer function becomes Kp exponential of e to the power minus TdS divided by tau Ps plus 1. This is called first order plus date time system. This is called first order plus date time system. Fine. Similarly, if we consider second order process, then the overall transfer function we can write as Z naught S equals Laplace transform of y t minus Td divided by Laplace transform of ft equals Kp exponential of minus TdS divided by tau square S square plus 2 zeta tau S plus 1. This is the second order plus date time system. This is called second order plus date time system. Fine. Now, we want to represent graphically the first order and second order plus date time systems. This is time and this is suppose y. This is the steady state of y. So, this value is representing y SS, that means steady state value of y. Now, if there is no date time, then the response is like this. If we disregard the date time, then the response is like this. This is the response of first order system. And if we consider the date time, then it becomes like this. So, this is the first order process response with introducing a step change in input variable. This is the first order dynamics with introducing a step change in input variable, and this is the dynamic representation when we disregard the date time. So, no date time, I mean no Td. So, this difference is the date time. Fine. So, this is the dynamics of first order system with date time and without date time. Similarly, if we consider the second order system, this is time, this is y. This value is the steady state value of y. Then for the second order system, we get this type of response. Definitely this is the second order underdamped response when zeta less than 1. If there is dead time, then the response is like this. So, this is representing the second order process response. Fine. This is the dynamics of second order response when there is no dead time, and this is the dynamics of second order response when dead time is there. Fine. Now, it was discussed earlier that, and we commented that it is convenient to represent the transfer function as the ratio of two polynomials. It is easy to analyze the transfer function by representing it as the ratio of two polynomials. And that is like G naught s equals Qs divided by Ps. If we represent the transfer function by this form, it is easy to analyze. Now, if there is a dead time, then how we can represent the overall transfer function by the ratio of two polynomials, that we will discuss next. So, our title is polynomial approximation, polynomial approximation to the dead time term, I mean exponential of minus TDS. So, we can approximate this exponential term by per day approximation. By per day approximation, we can approximate the exponential term. The forms are like this: exponential of minus TDS is approximately equal to 1 minus TD divided by 2 S divided by 1 plus TD divided by 2 S. We can write the exponential term by this form, and this is called first order per day approximation. This is called first order per day approximation. Fine. Similarly, if we can write the form as second order per day approximation, 1 minus TD divided by 2 S plus TD square S square divided by 12, 1 plus TD divided by 2 S plus TD square S square divided by 12. We can write the exponential term by this form, and this is called second order per day approximation. Fine. By another way also we can approximate, that is Taylor series expansion. By Taylor method also we can approximate this exponential term. So, that is the second method. Taylor series expansion. According to this, the exponential of minus TDS is approximately equal to 1 minus TDS. Exponential of minus TDS is approximately equal to 1 minus TDS. This is also first order approximation. This is first order Taylor approximation. First order Taylor approximation. It has another form, the Taylor method. By using Taylor method we can write this as 1 by exponential of TDS which is equal to 1 divided by 1 plus TDS. Exponential of minus TDS equals 1 by exponential of TDS, and that is equal to 1 divided by 1 plus TDS. This is also first order approximation, first order Taylor approximation. Fine. In the next we will discuss in reverse way, I mean how we can represent the higher order transfer function to lower order transfer function, that we wish to discuss. Approximation of higher order transfer function to lower order transfer function. Fine. Next we wish to discuss the approximation of higher order transfer function to lower order transfer function. But why we will go for this? By doing this we can easily design the controller. So, the first advantage is by performing the approximation of higher order to lower order, we can easily design the controller. Fine. So, it is easy to design the controller by transforming higher order transfer function to lower order transfer function. Another advantage is also it is easy to analyze. It is easy to analyze the lower order transfer function. Fine. Now, we will just take one example to discuss this approximation. We will take one example to discuss this transformation. Suppose the overall transfer function is given for a particular system by this form. GS equals the process gain Kp minus 0.2s plus 1 divided by 6s plus 1 multiplied by 3s plus 1 multiplied by s plus 1. To discuss the transformation of higher order to lower order transfer function, we have taken this example having the overall transfer function of this. Now, we wish to transform this transfer function to a first order plus date time system. So, we wish to transform this transfer function in the form of Gs equals Kp exponential of minus Tds divided by tau Ps plus 1. So, this is higher order transfer function, and our purpose is to transform this to lower order transfer function. Fine. Now, this we can do by the use of Taylor method. So, first we will use the Taylor method. Now, according to the Taylor method, minus 0.2s plus 1 is approximately equal to exponential of minus 0.2s. Agree? According to the Taylor method, we can write minus 0.2s plus 1 is approximately equal to exponential of minus 0.2s. Similarly, we can write 1 divided by 3s plus 1 approximately equal to exponential of minus 3s. Again, we can write 1 divided by s plus 1 equals exponential of minus s. Fine. Now, retaining the dominant time constant, retaining the dominant time constant, what is that? That is equal to 6. We get Gs equal to Kp exponential of minus 0.2, another one is 3, and third one is 1 multiplied by s, and the largest time constant remains in the denominator. So, can we write this from the higher order transfer function? So, it becomes Kp exponential of minus 4.2 s divided by 6s plus 1. So, this is the representation of higher order transfer function by the first order plus date time system transfer function. Fine. This is one method. Another method we want to discuss, that is Skogestad half rule method, using which we can also transform the higher order transfer function to lower order transfer function. So, next we will discuss another technique, that is Skogestad's half rule. The overall transfer function which we have taken is represented, again I am writing that, divided by 6s plus 1, 3s plus 1, s plus 1. Now, we will transform this transfer function to first order plus date time system by the use of Skogestad half rule. So, what is the highest neglected time constant? The largest neglected time constant considered in the Taylor method is equal to 3. Fine. In the earlier discussion, we have neglected this time constant, which is largest one. Now, according to this Skogestad's half rule, half of this, I mean 1.5 is added to the next largest time constant. Try to remember the step. In the Taylor method, the largest neglected time constant considered is 3. According to the Skogestad's half rule, 50% of this value, that is 1.5, is added to the next largest time constant, to the next largest time constant. What is the next largest time constant? 6. Next largest time constant is 6. That means the time constant becomes 6 plus 1.5, that is 7.5. Fine. The time constant becomes 6 plus 1.5, that is 7.5, and the other half provides a new time delay, provides a new time delay of 1.5. That means another half is considered as time delay, that will be added within the exponential term. Then what will be the reduced transfer function? According to this half rule, the transfer function finally becomes Kp exponential of minus 0.2 is there, half of 3, that is 1.5 is added, and 1 remains there. The time constant is already obtained 7.5. So, the denominator becomes 7.5s plus 1, that means Kp exponential of minus 2.7s divided by 7.5s plus 1. It has been observed that this transfer function obtained by the use of Skogestad half rule provides better performance than the transfer function obtained by the use of Taylor method. Fine. It has been observed that the performance provided by the reduced transfer function obtained by the use of Skogestad half rule is better than the response provided by the reduced transfer function obtained by the use of Taylor method. Fine. So, next we will discuss the dynamics of processes having inverse response. Next we will discuss the dynamics of processes having inverse response. These type of processes also provide nth order dynamics. Now, this type of behavior is observed when there exists a positive 0. This is the main point associated with this topic. This type of behavior, I mean the inverse response behavior, the inverse response behavior is observed when there exists a positive 0. When there exists a positive 0. Fine. So, we will consider a process, we will consider two processes acting in parallel. We will consider two processes acting in parallel. One has the transfer function of k1 divided by tau p1s plus 1. Another one has the transfer function of k2 divided by tau p2s plus 1. Now, we want to find the condition at which this process shows inverse response behavior. We wish to find the condition at which this process provides inverse response behavior. So, input to this process is f bar s and output of this process is y bar s. Fine. The two processes are acting in parallel. Now, first we need to find the overall transfer function of this process. The overall transfer function y bar s divided by f bar s, which is equal to k1 divided by tau p1s plus 1, sorry, this is kp1, and another transfer function is kp2 divided by tau p2s plus 1. Fine. Now, we get from this kp1 plus kp2 multiplied by kp1 tau p2 plus kp2 tau p1 divided by kp1 plus kp2 plus 1 whole divided by tau p1s plus 1 tau p2s plus 1. Fine. We get this transfer function, this overall transfer function. Now, we can represent again this as kp multiplied by tau s plus 1 divided by tau p1s plus 1 multiplied by tau p2s plus 1, where kp is kp1 plus kp2, where kp is kp1 plus kp2 and tau is Kp1 tau P2 plus Kp2 tau P1 divided by Kp. This is the tau. So, for positive 0, tau should be less than 0. Agree? For positive 0, tau should be less than 0. That means we can write Kp1 tau P2 plus Kp2 tau P1 less than 0. Agree? So, rearranging this again, we obtain Kp2 divided by Kp1 greater than tau P2 divided by tau P1. Rearranging, finally we get this condition. So, at this condition the process shows inverse response behavior. So, inverse response is the net result of two opposing effects. If you see the sign, tau P1, tau P2 both are positive. So, if one Kp is positive, another Kp should be negative. So, we can conclude that inverse response is the net result of two opposing effects. Fine. Thank you.